Okay, so we're going to start with just a few of these problems from lesson 53 that we didn't quite get to. So remember, when you raise a power to another power, you multiply the exponents. So when we raise 3x to the negative 2y to the fifth over z to the fourth to the negative 2 power, we're going to distribute that exponent to all the exponents in the parentheses. And we're going to multiply them. So remember that 3 is not an exponent, it is a base. So we don't multiply 3 by negative 2. We raise 3 to the negative 2 power. So when we distribute that negative 2 power to all the exponents in that parentheses, this is what it looks like. We have 3, just a second. We're going to have 3 to the negative 2 power. And then we're going to have x to the negative 2 times negative 2, which would be to the fourth. And then we're going to have y to the fifth raised to the negative 2. So we multiply 5 times negative 2 and get negative 10. And then the z is to the fourth, so we multiply 4 times negative 2 and get negative 8. So those are the exponents we have. Now we have the 3 to the negative 2 power, and we don't want to leave a constant with a negative exponent on it because we want to be able to evaluate that constant at that exponent. So if we have 3 to the negative 2, that means we can move that 3 down to the denominator and make it 3 to the positive 2, which is 9. So that's what I did in this last step. I left everything else where it is, and I just moved that 3 to the negative 2 down to the denominator, so it will become 3 to the positive 2, which is 9. So whenever you have a constant that's raised to a negative 2, or a negative power, you're going to need to move it so that it has a positive power, and then go ahead and evaluate it, whatever it is. All right, so this next one, you've got 2a to the negative 2b squared, z to the negative 10th, and it's all raised to the negative 5th power. So you're going to raise everything in there to the negative 5th power, which means you're going to multiply all the exponents by negative 5. Now, 2 is not an exponent, it's a base, so we're raising it to the negative 5 power. So we're going to have 2 to the negative 5th, then a to the negative 2 times negative 5, which is a to the 10th. And then we're going to have b to the 2 times negative 5, which will be b to the negative 10. And then z to the negative 10 times negative 5, which is z to the 50th. We're going to multiply the exponents when we raise it, when we raise a power to another power. And then again, you've got 2, which is a constant, raised to a negative exponent. So you're going to want to rewrite this with that 2 to the negative 5th. You're going to move it down into the denominator. So it becomes 2 to the positive 5, which is 32. So you just, anytime you have a constant like that, you need to get that, put it where it will have a positive power, and then evaluate it. 2 to the 5th power is 32. All right, here we've got 4xy over m to the negative 2, and then we're squaring that whole thing. That means that we have to distribute that 2 to all the exponents in the parentheses, and we multiply the exponents. All right, so we're going to have, for this one, we're going to have 4 squared. We're going to have x squared. We're going to have y squared. And we're going to have m to the negative 2, and we're going to multiply negative 2 times 2 to get negative 4. Okay, so the 4 is squared, so we can evaluate that. 4 squared is 16. Everything else can just stay where it is. All right, we've got this next one where we have 3x to the 0y over k to the 4th, and we're raising it all to the 3rd power. So that 3, that 3rd power, has to be distributed to all the exponents in the parentheses. First of all, x to the 0 is 1, so we can just go ahead and change it to a 1. So we'd have 3 times 1 times y, which is just 3y. So that 1 kind of just doesn't even need to be there, because when you multiply something by 1, it doesn't change anything. All right, so we've got 3 to the 3rd power. We've got y to the 3rd power. And then on the bottom, we've got k to the 4th raised to the 3rd. We multiply 4 times 3, and we have k to the 12th. So now we just need to evaluate 3 to the 3rd, which is 27, and we're done. All right, conversions of volume. Just like with area, when we have to use a unit multiplier twice in order to cancel square units, now if we want to cancel out cubic units, we're going to have to use the unit multiplier 3 times. So I have 180 cubic feet, and I want to change it to cubic inches. So all I have to do is remember, first of all, that there are 12 inches in a foot, And since I want to multiply this by something that will cancel the feet and leave me with inches, I'm going to put the feet on the bottom for my unit multiplier. So we're going to have 12 inches over 1 foot, and I'm going to use that unit multiplier 3 times so that it will cancel cubic feet. So it's like feet, feet, feet. Going to cancel the feet, 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 and be left with inches, 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 which is cubic inches. So I have to multiply by that unit multiplier 3 times, and I used an exponent to show that. So I end up with 180 times 12 times 12 times 12 cubic inches. All right, use 6 unit multipliers to convert to 800 cubic centimeters to cubic feet. So I'm starting out with 800 cubic centimeters, and then I'm going to need to multiply that by the conversion, the unit multiplier that changes inches or centimeters to inches. So there's 1 inch in 2.54 centimeters. I put centimeters on the bottom because I want to cancel the centimeters, and I'm going to have to do this 3 times, multiply it by 800 cubic centimeters 3 times to get rid of the cubic centimeters and end up with cubic inches. And then the next thing I'm going to have to do is change those inches to feet by multiplying by the unit multiplier 1 foot over 12 inches. And so that will cancel the inches because I'm going to do it 3 times. 1 over 12 times 1 over 12 times 1 over 12. I'm going to do it 3 times to cancel the cubic inches, and I'll be left with cubic feet. So all the things that I don't want are going to cancel out, and I'm going to be left with cubic feet. All right, so lesson 54 is starting out talking about the substitution axiom. And the substitution axiom just says that if 2 expressions A and B are of equal value, that is if A equals B, then you can replace A with B in any expression without changing the value of the expression. You can substitute A for B. You can replace B with A in any statement without changing the truth or falsity of the statement. You can also replace A with B or B with A in any equation or inequality without changing the solution set. Okay, so it's just a long way of saying, anytime you want to, if you have 2 quantities that are equal to one another, you can substitute them for one another. And we're going to use that axiom to find the solution sets for systems of 2 equations and 2 unknowns, 2 linear equations. When we want to solve a system of equations, and you can tell this is a system of 2 linear equations because it has that curly bracket next to it. And when it says to solve that, what it means is we want to find the coordinate pairs that would work in both equations at the same time. All right, so for example, you could look at these equations and you can see that the point 3, 5 is a solution of the first equation, because if you put in 3 for x in that first equation and you put in 5 for y, you get 2 times 3 minus 5 equals 1, and 6 minus 5 does equal 1. So 3, 5, that point works in the first equation in this system. But does it also work in the second equation? Well, let's see. Let's put 3, 5 into the second equation. We're going to put in 3 for x and 5 for y, so we'd have 3 equals negative 3 times 5 plus 11. And if you work that all out, you get that 3 equals negative 4, and 3 does not equal negative 4. So no, that point doesn't work in the second equation. So what are we going to do to figure out the solutions that will work in both equations? All right, so that's what we're trying to do here. And to do that, we're going to use the substitution axiom. So if I have a set of simultaneous equations like this, I have 2 equations, they're both linear, 2 equations and 2 unknowns, x and y. So I've got 2x minus y equals 1, and I've got x equals negative 3y plus 11. And I'm looking for the pair, the xy pair, that will be true, that will make both equations true at the same time. So We're trying to solve the equations simultaneously. And the way we're going to do that is that if you look at the second equation, it says x equals negative 3y plus 11. So in the second equation, we have x. We know what x equals in terms of y. It equals this. So what we're going to do, because of the substitution axiom, we know that we could substitute that amount into the other equation for x because those two things are equal, and we know that we can substitute two equal things. We can substitute one for the other. So in the first equation, I'm going to take wherever I see an x, and I'm going to put that amount, negative 3y plus 11, into that first equation for x. So that's what I'm going to do. Now, I'm going to rewrite that first equation, except for wherever I see x, I'm going to put negative 3y plus 11 because that equals x. So I can substitute it. So I get this equation. I'm rewriting the first equation, 2x, so it's 2 times negative 3y plus 11, putting it in parentheses because I want to multiply that whole thing by 2 because that whole thing is x, then minus y equals 1. Now all I have to do is use the distributive property to distribute that 2, so I'll get negative 6y plus 22 minus y equals 1. Now I'm going to combine my like terms. I've got negative 6y minus y, so that's going to be negative 7y plus 22 equals 1. Now I can subtract 22 on both sides, and I will get that negative 7y by itself. So negative 7y equals negative 21, and now I will divide both sides by negative 7, so y would be 3. So I figured out what y is. Now I need to figure out what x is. So I'm going to take this value I got for y, and I'm going to put that into the second equation wherever I see a y. So x equals negative 3 times y plus 11. That's the second equation. I'm going to now put in 3 for y in that equation. X equals negative 3 times 3 plus 11, so x equals negative 9 plus 11, which is 2. So the value 3 for y and 2 for x will work in both equations, because if I plug that into the first equation, if I put in 2 for x, I'm going to get 4 minus, and then I put in 3 for y, so I get 4 minus 3 is 1, and that works. And then the second equation, if I put in 2 for x and 3 for y, I've got 2 equals negative 3 times 3, which is negative 9, plus 11, and that's true. 2 equals negative 9 plus 11, that's true. So they work, the point works in both equations, so the solution is the ordered pair 2, 3. X is 2, y is 3. So that would be the solution to that system of equations. That is the point. That is the coordinate pair that will work in both equations. All right, here's another one. 2x plus 3y equals negative 13. Y equals x minus 6. So again, now I have y is solved for in the second equation. I know that y is x minus 6. So I can take x minus 6 and I can plug that in to the first equation for y because it equals y, and so I can substitute it for y. So I'm going to rewrite the first equation, substituting x minus 6 wherever I see y. So 2x plus 3 times, instead of a y, I'm putting x minus 6 equals negative 13. Now I can use the distributive property. 2x plus 3x minus 18, you've got to distribute that 3, equals negative 13. Now I can add my like terms. 2x plus 3x is 5x, minus 18 equals negative 13. And then I can add 18 on both sides. 5x equals 5, divide by 5 on both sides, and x equals 1. So if x equals 1, I can take that amount and plug it back into the second equation for x and see what I get for y. So y equals 1 minus 6, which is equal to negative 5. So the solution is the ordered pair 1, negative 5, because if you take those values and put them into both equations, it will work for both equations. It makes both equations true. All right, here's another one. I've got 3x plus 2y equals 3 and x equals 3y minus 10. The second equation is solved for x, so I can take that amount, 3y minus 10, and I can substitute it into the first equation for x because it's the same as x. So I'll have 3 times x, which is 3y minus 10, plus 2y equals 3. Now I distribute the 3, 9y minus 30, plus 2y equals 3. Now I can combine by like terms. 9y plus 2y is 11y, minus 30 equals 3. Now I'm going to add 30 to both sides of the equation. 11y equals 33. Now I'm going to divide by 11, so y will equal 3. Now I know what y is. I can plug that into the second equation to figure out what x is. So x equals 3y, or 3 times 3, minus 10. 9 minus 10 is negative 1, so this is the ordered pair you would get. Negative 1 for x, 3 for y, and if you plug those values into both equations, it works in both equations. It makes both equations a true statement. All right, one more. Here we've got negative x minus 2y equals 4 and y equals negative 3x plus 8. So the second equation tells me what y is. Y is negative 3x plus 8. So I'm going to take that amount, negative 3x plus 8, and I'm going to plug it into the first equation for y. I'm going to substitute it for y. So the first equation will look like this, because where I see a y, I'm going to put negative 3x plus 8. And now I'm going to use the distributive property to distribute that negative 2. Make sure that you carry the negative with it to both terms inside the parentheses. So you'll have negative x plus 6x minus 16. So be careful with that. Equals 4. Now I'm going to combine my like terms. Negative x plus 6x would be 5x. Minus 16 equals 4. I'm going to add 16 on both sides. 5x equals 20. Divide by 5, and x equals 4. So we know that x is 4. And so we're going to use that amount and put it into the second equation for x. So we'll have y equals negative 3x, which is 4, plus 8. So y equals negative 12 plus 8, which is negative 4. So now we know that the solution to this system of equations is the ordered pair for negative 4. X is 4, y is negative 4, so that is the solution. All right, so you use substitution to solve these systems of two equations by just taking one of the variables and figuring out what it is, and then substituting that into the other equation.